Hi, in this STR8CHEM session, we're going to look at polarity. So in polarity, we're going to think about, is it polar or is it a non-polar molecule? So we have learned about how to draw the most plausible Lewis structure. And also you have learned about how to determine the shapes of the molecule. And after you have learned those things, you should be able to identify whether the molecule is going to be non-polar or polar molecule. Just now I've mentioned that you need to know Lewis structure. So first of all, you need to identify the correct Lewis structure. And then after that, you need to be able to determine the correct molecular shape. And therefore, you would be able to identify the polarity of your molecule. So if you don't know how to identify this and this, it would be difficult for you to know this one. Okay, so it's better for you to learn this one first, and after you have mastered how to identify the most plausible Lewis structure, you would be able to identify the correct molecular shapes, and you would be able to do this polarity right over here. Okay, so to start learning about polarity, first of all, you need to know, what does it mean by polar bond? You need to identify the polar bond in your molecule. You need to know whether your molecule has a polar bond or not. So I'm going to take one example over here, a few examples. So we're going to start with bromine molecule. So we know that bromine molecule is like this. Okay, so two bromine atoms are connected with a covalent bond, okay, with a single bond, and you have the lone pair surrounding the both of the bromine atoms. So to identify whether this bond over here is polar bond or not, first of all, you need to know what is the electronegativity for both bromine atoms. Okay, so when you look in the periodic table, okay, so I'm going to open up bromine over here. So the electronegativity for bromine atoms is 2.96. So both of them will have, this one is 2.96, that one is 2.96. So both of them will have the same electronegativity. Therefore, this is a non-polar bond because it is shared by two atoms with the same electronegativity right over here. Therefore, that covalent bond is a non-polar bond. And overall, what you have here is a you will have a non-polar molecule. So a non-polar molecule will have a dipole moment equals to 0. So that is the dipole moment equals to 0. So I'm just gonna redraw that again. So the symbol is like this, okay, equals to 0. So let's have a look at another example. So if we have this molecule. Okay, so the Lewis structure would look like this. H connected to a bromine atoms through a single bond right over here. Okay, so if we want to identify whether that bond is going to be a non-polar bond, we have to look at the electronegativity, but even without looking at your periodic table, you should be able to identify that this bromine over here will be more electronegative because it is situated at group 17, and then this HSM over here will be less electronegative because it is situated in group 1. Okay, so we know that this one will be partially negative because bromine atom is situated on group 17, and that one will be partially positive. So when you have this situation like this, okay, then we would say that this bond over there is going to be that bond over here is a polar bond, because this bond is shared by two atoms with different electronegativities. So if you want to have a look at the real data, so now just now for bromine, the electronegativity is 2.96. Okay, so what about H, hydrogen atom? So the electronegativity is about 2.20. So that's a difference over there. So the electronegativity over here is 2.96. That one is 2.20. So when you look at this data, you can identify that this is the polar bond, and then you're gonna show that the polarity is like this by using this arrow. So you're gonna show that the electron density is more towards the more electronegative atom right over here. Okay, so this symbol over here is very important for you to show that this bond is a polar bond. If they want you to show the polarity, you have to show this symbol over there from the more electropositive or less electronegative atom towards the more electronegative atom right over here. Okay, so just now we have identified that HBr is a polar molecule. Okay, you have a polar molecule over here because it has a polar bond. Therefore, the dipole moment is not equal to 0. That is very, very important. Okay, sometimes you have let's say if you take carbon dioxide, sometimes you have molecules that have polar bonds, but they will become a non-polar molecule. Why? Because the polar bond will cancel out each other. For example, right here, carbon dioxide, we do know that the shape of carbon dioxide is linear like this. Okay, and between carbon and oxygen, carbon is situated in group 14, oxygen is situated at group 16. Therefore, oxygen atom will be more electronegative, this one will be more electronegative, and carbon will be more electropositive because carbon is situated in group 14. Oxygen is situated in group 16. Remember, in chapter 3, we learn about periodic table. If you move across the period, the electronegativity will increase. So oxygen will be more electronegative than your carbon. If you want to have a double check on the periodic table, okay, carbon over here, the electronegativity of carbon is 2.55, okay? So you maybe want to write that. So this is 2.55 for carbon. And then for oxygen, the electronegativity here, okay, is 3.44. So that is a very clear difference in electronegativity, okay? So remember, you have to put this arrow to show the polar bond from the more electropositive atom towards the more electronegative atom, and then another one going that side. Right, so in this case, CO2 has polar bonds, but the shape symmetrical, because you have linear and the polarity one is pulling that side, this polarity is pulling to the opposite sides, and it is symmetrically it is in symmetrical shapes over here. Therefore, the polarity will cancel out one another. You have a non-polar molecule. Therefore, the dipole moment is equals to 0. Okay, so in exams, you have to show this polar bonds over here with that symbol. You get 1 mark. You're going to tell them it has a polar bond. You have 1 mark. You're going to tell them it is symmetrical. 1 mark. Therefore, it's a non-polar molecule, and dipole moment equals to 0, 1 mark. Okay, so that's why I said it's very important for you to be able to know how to draw the most plausible Lewis structure in the beginning, because from there you would be able to know what is the correct molecular shapes, and from that shape you will be able to identify whether your polar bonds going to cancel out one another or the other way around. Okay, so let's have a look at more examples. So let's say we're going to have CCl4. Okay, so the structure for CCl4 is something like this. Have chlorine. It's in tetrahedral shape. Okay. So the molecular shape is tetrahedral. I'm gonna write that again. Okay. And then we have to identify, does it have polar bonds? So when you look here, you have carbon and you have chlorine, 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 and chlorine. Okay, so your carbon over here is obviously going to be partially positive. Okay, because it is situated in group 14, and then chlorine atoms is situated in group 17. Thus, that one is going to be partially negative, partially negative, partially negative, partially negative. Okay? So, it's obvious that this has 4 polar bonds. Okay? So, it has polar bonds. Okay? From that here, when you show that in exams, you're gonna have 1 mark. Obviously, 1 mark for the correct molecular shapes, 1 mark for telling them it has polar bonds. But when you look at the structure as a whole, is it symmetrical? Yes, it is symmetrical. Okay? Because all of the angle over here, if you still remember, all of the angle over here will be the same. Okay? All of the angle will be the same. So, this one is it's a symmetrical molecule. Therefore, it will be non-polar molecule, and the dipole moment is equals to 0. Okay, when you have a symmetrical molecule, the electron density will be equally distributed on the molecule over here. So when the electron density is equally distributed, therefore the molecule will have a dipole moment equals to 0. This is what we call as the dipole moment. Okay. Now, so let's have a look at another example. We're gonna look at okay, now let's have a look at another example, shall we? So let's say we have CCl3F. So you have carbon in the middle, fluorine right over there, chlorine, and chlorine. The molecular shape is tetrahedral, and we do know that this is partially positive, this is partially negative, partially negative, partially negative, partially negative. Okay, because fluorine over here is also on group 17, group 14, therefore this is more electropositive than your fluorine and your chlorine right over there. And the polar bonds will have that direction. So you get 1 mark for that, 1 mark for this. So it has polar bonds. Okay, get another 1 mark for that one. But right now, is it equally distributed? Since this over here has a different electronegativity than this, that, and that. Therefore, this it is A and S. We're going to use the word it is a non-symmetrical molecule. Okay, because you have this, it has a different electronegativity, then that's why it is non-symmetrical, because the electron density is not equally distributed on the molecule. You can have a look at the chlorine just now. When we look at the chlorine, so the electronegativity for chlorine is about 3.16. okay, chlorine has 3.16, and fluorine would be about 3.98. okay, so you have 3.98 over here. So you have 3.98. So fluorine is more electronegative than your chlorine atoms over here. Therefore, you have a dipole moment going up there. So that is the dipole moment right there. Okay, so the dipole moment is not equal to 0. Therefore, this is a polar molecule. Okay, so what about another example? So let's have a look at another example. So if we have CH2Cl2, okay, so carbon, you have H going that direction, H, Cl, Cl. So the shape is tetrahedral. Then you know that this is partially positive. Okay, if compared to this, you have partially negative. So the polar bond is going that side. But if you compare, this is partially positive, that one will be partially negative. So the bond polarity will go that direction. This one is partially positive, that one is partially negative. So the bond polarity is going that direction. Okay, in this case over here, it does have polar bonds. And if you look at that side, you have 2Cl, pulling the electron density to that direction, and then you have 2H over here, which is more electropositive than carbon, so the carbon will pull electron density to that direction. So you can see that this one is asymmetrical molecule. Why? Because the electron density is equally distributed on the molecule. Okay, so when that is a symmetrical molecule, you do not have a resultant dipole moment. So you have dipole moment equals to 0. This one is a non-polar molecule. Okay, so you will get 1 mark for those signs being shown, and the partially positive and partially negative. 1 mark for the shape, 1 mark for telling them it has polar bonds, 1 mark for this, 1 mark for that, and 1 mark for this. Okay, so let's say if we have molecules with lone pairs. So let's say H2O. So the shape for H2O is oxygen. You have H, you have H, you have lone pairs. So the molecular shape is bent. So we know that this is partially negative, that one is partially positive, and partially positive. So the bond polarity gonna go that side. So we know that it has polar bonds. It has polar bonds. But is it equally distributed? No. So the resultant dipole moment is going that direction. So that is the resultant dipole moment, okay? So that is the resultant dipole moment, which is not equal to 0. Okay? So why is it non-symmetrical? Because the electron density is not equally distributed on the molecule. So we have not equal to 0. So this is a polar molecule. Okay. Another one. we have a ammonia NH3, okay, so the shapes should be about N, H, H, and H, and you have a lone pair over here, and we do know that this is partially negative, partially positive, partially positive, partially positive. So the bond polarity is going that direction. So when you look here, it is not symmetry, is asymmetrical. So the resultant dipole moment is going up. So this is the resultant dipole moment, which is not equals to 0. So it is indeed a polar molecule. So the shape is trigonal, pyramidal. It has indeed polar bonds, but it is a non-polar molecule because the electron density is not equally distributed on the molecule. So we're gonna have a look at another examples. For example, if we have something like SF6, okay, so you have sulfur, so the molecular shapes is octahedral, and sulfur, if we look at the data, fluorine is 3.98, sulfur is about 2.58. So sulfur is partially positive, this is partially negative, partially negative, partially negative, partially negative, partially negative, partially negative. So the bond polarity is going that direction. Okay, so it has polar bonds, but it is a symmetrical molecule. Why? Because the electron density is equally distributed on the molecule. So the dipole moment is equals to 0. This one is a non-polar molecule. It does not have a resultant dipole moment. Okay, so that's how you're going to identify whether your molecule is going to be polar or non-polar. First, you try to identify the Lewis structure and the molecular shapes, and then look for polar bonds, and then look at whether the electron density is equally distributed or otherwise. Okay.